Hi everyone, in this video we're going to be doing A-Level Maths 9709, Paper 41, Mechanics, October, November 2025. This paper is 1 hour 15 minutes long, so we'll try to finish within the time limit. So without further ado, let's get started. Okay, so for the first question, we are told that a car of mass 900 kg is moving along a straight horizontal road against a constant resistance to motion of 350 newtons. So this is the resistive force. At an instant, when the car is moving at 15 meters per second, acceleration is 0.25 meters per second squared. Okay, so for the first part, we need to find the driving force of the car's engine at this instant. So the instant that they're referring to is the last sentence. Okay, so to do this question, let's first draw a diagram. Okay, so let's say our car is moving here, right? So the driving force, I'm gonna call it F, is obviously in this direction, and the resultant, the resistive force is opposite to it. So 350 newtons. Okay. All right. So we are told that it's accelerating at 0.25 meters per second squared. So if there's acceleration, that means this F is not equal to 350, and instead we're going to have to minus F and 350 together. With minus F first because it's moving in this direction. And this one, we will make it equal to m times a, where m is the mass and a is the acceleration. Okay, so let me substitute everything. So 900 times 0.25. Okay, now just add everything up. You will get 575 newtons. So this would be our final answer for the first part. Let's move on to the next part. Okay, so for this second part, we are told to find the power of the car's engine at this instant. So the instant they're saying is that the car, when it's moving at 15 meters per second. Okay, so to find the power of any object, you have to know this formula, force times velocity. So to know this formula, you can take the original formula, E over T, and energy, we know that is equals to work done, and work done is force times distance over T. And then you can take out the F, and then you'll be left with D over T. Sorry, and then you would have, and we know that D over T is just V, so you'll get P equals to FV. So I just showed how to derive this formula if you can't remember during the exam, but it should be pretty easy to remember. Okay, right. So we just need two pieces of information, the force. In this case, since we want to find the power of the car engine, we have to find the force that is being exerted by the car engine, which is basically just the driving force we found in the previous part. So that is 575. And then velocity, we're told here already, 15 meters. So 15. Okay, and then now you multiply, you would get 8,625 watts. So yeah, you can also leave it in kilowatts, but you have to round it off to 3 SF. Or you can leave it like this because it's exact. So in kilowatts is 8.6 25 kilowatts. Yeah, so yeah, these would be our final answers for this part as well as the entire question. Let's move on to the next question. Okay, so for this second question, we are told that two particles P and Q of masses 3 kg and 5 kg respectively are at rest. So this is a keyword on a smooth horizontal plane. So there's no inclination. P is projected at a speed of 4 meters directly towards Q. So this second part tells us the speed and the direction that P is going in initially. So this for P. And then it says in the last sentence, after P and Q collide, P has speed 1 meters. Okay, so for the first part, we need to find the two possible speeds of Q after the collision. So first of all, why do you think that there is two possible speeds that Q can have? Well, we know that momentum is dependent on direction. So obviously, after the collision, there can be two possible directions, and therefore two possible speeds that Q can go through. So first step for any momentum question, you want to draw the scenario. So before collision, let's draw that out. So the main purpose of this is to see what direction P and Q are heading into. Okay. So before it says that P and then Q. So P is projected towards Q at 4 meters per second. And then Q is at rest. So Q is stationary. And then after that, P and Q collide. P has speed 1 meters per second. However, they didn't really specify the direction. So we're going to have to guess, kind of. Okay. Right. So for case one, so I'm gonna write here after case one. Oh sorry. Q, oh sorry. Q can either move in this direction, and if Q moves in this direction, then P can okay, so okay. All right, so Q can be here. No, Q can go this direction, then P can also follow behind. So this is 1 meters. Uh, or after case number 2, Q can go in the opposite direction. Actually, that wouldn't make sense. Yeah, never mind. So yeah, Q cannot move in the other direction. Q can only move in this direction. So P will be the one that moves in the other direction instead. Okay? All right, so before we begin solving, we have to denote which direction we assume to be positive and which one to be negative. So I'm going to assume that this is positive and the opposite direction is negative. So everything towards the right is positive and everything towards the left is negative. All right, so now we can start. So let's find the total momentum before. So that will be 4, which is the speed of P. 4 times 3, the mass of P, plus 5, which is the mass of Q, times 0, which is the speed. And that would be equal to, okay, this is for case 1. That will be equal to P, that is 3 kg, and then 1 kg, and then plus Q is also moving in the same direction, so that's also positive. So Q, that would be 5 VQ. Okay, so just solve everything. So 3 plus 5 VQ, you'll get 12. And then 5 VQ, you will get 9. And then VQ, you would get 9/5 meters per second. So that's for case 1. And case 2, yeah, the same initial velocity, initial total momentum, and you equate it to P. So P is 3 times. In this case, it's moving towards the left, so the velocity here will be -1. And then plus VQ. So simplify everything again. So 5 VQ minus 3. I'm swapping the left and right sides. So 12 times 0, that is 12. 5 VQ, you'll get equals to 15. And therefore, VQ would be 3 meters per second. So yeah, these would be our final 2 speeds for Q. And we can move on to the next part. Okay, so for this second part, we are told that lambda joules of kinetic energy, where lambda is more than 0, is lost during the collision. So we need to find the value of lambda. Okay, so to do that, let's find the total KE before and after. So let's find before first. So before, P was projected at 4 meters towards Q. So that means Q was stationary, so it had no KE. So we only have to find the KE of P. So that's half mv squared. So m for P is 3 kg. You can see here. And the speed is 4 meters, so 4 squared, v squared. And so now just type into your calculator. So 8 times 3, that is, 16 times half, that's 8. 8 times 3, that's 24. So 24 joules. That was before. Now let's find the total KE after. So for the total KE after, because we have 2 possible speeds for Q, so naturally there would be 2 values of the new KE. Okay, so let's find both of them and then we'll figure out which one it is. Okay, so after P and Q collide, P has speed 1 meter. So find the KE of P, so half m, that is 3 for P, v squared, which is 1 squared, and then plus that of Q. So Qm is 5. So obviously it has to be half times m, which is 5. And then the first speed, we're going to use 3. Okay, so that's one of the speeds for Q after the collision. Okay, so if we get a value that is less than 24 joules, we're not going to go ahead and calculate the other possible one. Okay, but you can do both if you want to be safe. Okay, so interestingly, we got 24 joules, but this can't be possible because they said there is some loss of KE and lambda is more than 0. So let's find the other total KE. It has to be the other one. So KE of P plus KE of Q version 2. So the other speed of Q is 1.8 squared. Okay. Now it definitely has to be lesser. Okay, so now we got 9.6 joules. So yeah, these are our two answers that we can use to get lambda. So just take the difference between the two KEs before and after, and you would get 14.4 as your final answer. So this is the amount of KE that was lost. And with that, let's move on to the next question. All right, so for this question, we are given these four forces in here. So it's also like stated here, coplanar forces of magnitudes these act in a point shown in the diagram. Find in either order, so we can do like you can choose whichever one you want to do, the magnitude and the direction of the resultant force. Okay, so main point here is we need to find the resultant force in here. So to start off with this question, like to make it simpler, we are just going to split all of the forces that are acting at an angle such as this, and this into vertical and horizontal components. Okay, so let's split them up into vertical components first and find the resultant force in the vertical direction. Okay, so this is the sign of vertical. Okay, so vertical, yeah, we have 45 newtons. Okay, 28 newtons as a component. Vertical component would be here. So 28 sine 35. Okay, and then for 72, that would be downwards. That's 72 sine 50. And finally, for 35 newtons, also downwards, it is 35 sine 70. Okay, so I'm going to take the upward vertical force as the positive direction. So I'm going to mention that first, and I will subtract the downward vertical forces. You can do it the other way as well. Okay. Okay, so let's do that. So 45 plus 28 sine 35 minus the downward, which is 72 sine 50 and 35 sine 70. So minus bracket 72 sine 50 plus 35 sine 70 degrees. Okay, all right. Okay. So, okay, just type into the calculator first. And make sure that your calculator is in degree mode for this. 72 sine 50 minus 35 sine 70. Okay, so unfortunately we get a negative answer, but don't panic. That just means that our guess wasn't correct. And then instead of the resultant acting upwards, it's actually acting downwards. And I believe you would have guessed that if you computed the total upward and downward force. But it's okay. Um, yeah, let's just keep it this way. All right. Yeah, we can't really simplify it and we don't get a nice answer. We're just gonna keep it as it is for the magnitude later on. Yeah, so this is it. Okay, you can leave it to 5SF if you want. Yeah, I guess I'll do that. So minus 26.984. Yeah, so this is our vertical resultant force. Now let's do for horizontal. Yeah, so for horizontal, we can completely ignore the 45. We're just going to focus on the other three, 28, 35, and 72. So for this direction, we have 28 cos 35, as well as 72 cos 50. So plus 72 cosine 50. And to the left, we have 35. Oh, wait. Oh, shoot. Uh, hmm. Oh, I just realized I made a mistake for the angle. Okay, so yeah, I thought this was 70, so it is not. So if you like do simple calculations, since this is a straight line, so 180 minus 70 minus 50, you would get 60. Yeah, so this is actually 60 degrees. So yeah, for our vertical force, this is 60. Okay, let me just erase that. Yeah, sine 60, 35 sine 60 for the vertical component. Right. So, okay, let me see if all the other angles are correct. Okay. Okay. All right. Okay. Okay. So we have, so as I was saying, the left side, that would be 35 cosine 60. Yeah. So horizontal be 28 cos 35 plus 72 cosine 50 minus 35 cos 60. So, I mean, for me, I like to leave it in exact form, but you can also leave it to a higher number of SF or decimal places if that's what you prefer. So I'm going to leave it to 5 SF for this one. Okay, so we get 51.717. And as for the vertical, um, it is, give me a while. Yeah, it's negative 24.406. And again, don't panic just because it's negative. It just means our previous assumption was wrong. Okay. Yeah, so these are the magnitudes of the resultant forces in the vertical and horizontal direction. All right. So yeah, let's take a mental note of the direction of the resultant force, like the components, the vertical component. So I'm going to use a different color. So for the vertical resultant force, it's acting downwards. You can use a double arrow to signify this. And for horizontal, Since this is bigger, this is positive, and we got a positive answer, so that means our guess is right. So therefore, the horizontal component would be in this direction, and therefore our resultant force would be something like this. Like the angle would be relative to this horizontal axis, and it will go clockwise. Yeah, like the angle would be clockwise from the um, horizontal axis. Okay, all right, so now let's find the magnitude. Okay, so magnitude, use your Pythagoras theorem. You can see it's a right angle triangle. If you just like move the components like slightly to the left, you'll see it's a right angle triangle. So yeah, use your Pythagoras. So answer squared plus 28 cos 35 plus 72 cos 50, 35 cos 60 squared. Okay, and then square root. You would get 57.2 newtons to 3SF. And this is the final answer, so I left in 3SF. Okay, now let's find the direction. So to express the direction, um, you have to, how do I say this? Uh, you have to like express the angle with respect to the horizontal axis and say whether it's below or like, okay, you have to say like which direction it is in, like whether it's clockwise or anti-clockwise from the horizontal axis, and on which side, the left side or the right side. So you have to be as detailed as possible. Okay, so to find the right angle, you can use the right angle triangle analogy, right? So yeah, if you do that, the angle would just be the tangent inverse of the vertical component divided by the horizontal component. Yeah, and you don't have to take in any signs. You can just divide by the magnitudes. Okay, right. So just doing a quick calculation. Okay, so downward is 24.406 divided by 51.717. Okay, and remember this should be in degrees, not radians. Okay, 72 sine 50 plus 35 sine 60 minus 45 minus 28 sine 35 over 28 cos 35 plus 72 cos 50 minus 35 cos 60. So this is 25.3 degrees. Okay, but this is not the final answer. We have to put a complete description. So we can say resultant force is at an angle of 25.3 degrees clockwise relative to the left side. Wait, no, right side, sorry. Right side of the horizontal axis. Yeah, so this is the best way I can put it. If you have any other way to put it, you can also put it that way, as long as it's detailed. Okay. So yeah, these two would be our final answers. for this entire question. Let's move on to the next question. Okay, so for this question, we are told that two particles A and B of masses mkg and 3 kg are connected by a light inextensible string. So they are connected particles. And particle B is on a fixed plane, which is at an angle of sine inverse 0.6 to horizontal ground. So you can see this is given in a diagram. This is the horizontal ground, and this is the plane. Okay. And the string passes over a fixed smooth pulley at the top of the plane. So this is the pulley they're talking about. Particle A hangs vertically below the pulley and is 0.75 meters above the ground. So that's also given here in the diagram. Okay, so in the second paragraph, we're told that the system is released from rest. And in the subsequent motion, B moves up a line of greater slope. So it goes up. So this is the direction of motion. And it does not reach the pulley. And as B moves up the plane, there's a constant resistance to its motion of magnitude 10 over 3 newtons. So that's most likely the friction, but it doesn't really matter here. And the speed of A immediately before it hits the ground is 2 meters. Okay, so B obviously has to move downwards since A is moving up. And right before it hits the ground, speed was 2 meters per second. So since, B and A are connected, logically B should also be moving upwards at 2 meters per second at that very instant right before A hits the ground. Okay? Yeah, so keep that in mind. And finally, we are told to use an energy method. So what this means is you cannot find the forces and then find the resultant force, use your Newton's second law. You have to use energy method. So you have to find the work done, KE, GPE, and all that to find the value of M. So this is very important. If not, you won't get the full marks. All right, so to use the energy method, we are going to use the principle of conservation of energy. So what that means is total energy before equals total energy after. So total energy is always constant. Okay. All right. So let's find the total energy before. And in this context, before is when it's at rest. So yeah, at the instant that it was at rest. So basically, this instance that they're showing us in the diagram without all the annotations. Yeah, so before it was released, they were obviously not moving, so there's no KE. However, both of them were above the horizontal ground. So the only energy that is truly there is the GPE of the two particles, B and A. So for B, it's a bit challenging since they didn't give us the height. But it's okay, we'll just say that it's at a height H. All right. Yeah, they didn't really say whether they're at the same horizontal level. We can't assume that. Okay, so yeah, B will take B to be at a height H. So the GP of B, MGH, M is 3, and then G, and then H, which is obviously just H, plus that of A. So A is MKG times G times 0.75. So you would get 3GH plus 0.75 mg. So this is the total energy before it was released from rest. Now after, so in this context, we're talking about this instant right before A hits the ground, the very last sentence. So at that instant, both B and A are moving at 2 meters per second. So obviously, there is kinetic energy. Okay, so let's account for that. So half, so for B is 3. So half M, which is 3 V squared, V is 2. So half mv 2 squared, so half times 3 times 2 squared, plus that of A, it's just half m, also 2 squared. Yeah, so this is the total KE. And we also have to keep in mind that since, B moved up, so let's say it was here, this is the position at that instant, its GPE isn't the same. So we have to also find the GPE at that new instant. Okay. So to find the new height, we know that at that instant, A should be right here. So A has moved this whole distance. And since B and A are connected, that means B also has moved this distance of 0.75. And using our basic trig, similar triangles, this angle is also the same as this. Yeah, so we can say that this height is just h. So until here is h plus this extra bit. So this extra bit, we can use the simple trigo. Okay, so 0.5 hypotenuse times the sine of this angle, which is the same. So sine inverse 0.6. So it's just 0.6. So h plus 0.75, 0.6. Yeah, so that's the new height. Okay, so plus m. So m is 3. Then h is h plus 0.75, 0.6. Yeah, so this is for B. And for A, we already established that it's at ground level, so it has no GPE relative to the ground. Yeah, so that's for B and A. And one last thing to note is that, the work done against the resistive force. Yeah, so you have to also take note of that, even though it is not in there. Like that's the energy lost. Okay, so if you take the difference between the energy before, energy after, you'll get the energy gained or energy lost. But since we're going to equate it, we have to account for the energy loss, which is the work done against the resistance. So resistance is 10 over 3. So work done formula is force times distance. So force is 10 over 3, and the distance would be the distance over that which B moved from when it was released from rest to here. So we've already found that out. It's just 0.75. And yeah, this is all for the total energy after. So yeah, type all the known terms into your calculator. So 6 plus 10 over 3 times 0.75. That's 5 over 2. And then half m2 squared. So half times 2 squared is 2. So plus 2m plus 3gh plus 3g times 0.75 times 0.6. So 3 times 0.75 times 0.6. That's 1.35 g. Yeah, okay, that's all the terms. So 6 plus 5 over 2, 8.5 plus 2m plus 3gh plus 1.35 g. So this is our total energy after. Now we're going to equate the before and after together. So 3gh plus 0.75 mg equals to 8.5 plus 2m plus 3gh plus 1.35g. So we can see we have, 3gh on both sides, so we can cancel those out. And now we're going to move all the m terms towards the left-hand side. So we'll move this over to the left. So 0.75 mg minus 2m equals to 8.5 plus 1.35g. Now we're going to factor out the m. So m times 0.75g minus 2 equals to 8.5 plus 1.35g. Yeah, now we'll just divide both sides by this to get our m. So now we're going to substitute g equals to 10. That's what you're supposed to do for all the mechanics papers in maths and further maths. So 8.5 plus 1.35g. So 1.35 times 10, that is 13.5 over 0.75g. So 0.75 times 10, you would get 7.5 minus 2. Okay, so okay, let me see if I missed out anything. I don't think I should have. Okay, so yeah, you get 4 as your final answer. So this would be our final answer for this entire question, m equals to 4. Let's move on to the next question. Okay, so for this question, we're told that a particle P of mass m kg is in equilibrium on a rough plane inclined at an angle theta to the horizontal. Yes, so it's given in the diagram here. The equilibrium, so this is the keyword, the equilibrium of P maintained by a force of magnitude 8 mg Newton, making an angle theta with the line of greatest slope. Yeah, so it's also given in the diagram. So this is the force that they're talking about. And this is the angle that it is acting at relative to the greatest slope. Okay, and the coefficient of friction between P and the plane is 0.5. So our mu is 0.5. And P is on the point of slipping down the plane. So this tells us that since it's going to slip down, the friction has to act up the plane. Okay, so I'll just label this as F. Okay, and we need to find the value of theta. Okay, so first things first, since we know it's in equilibrium, we have to first sketch out all the forces and equate the vertical and the horizontal components equal to each other. Okay, so for P, since there's mass, obviously downwards must have weight acting on it. So mg, yeah, and then friction, we already accounted for it. Okay, yeah, I don't think there's anything else. Yeah, it's just these three forces. Okay, now we're going to take the vertical equilibrium, okay? Like we're going to take the vertical components of all the forces. So let's do for, wait a minute. Um, okay, let's wait. Okay, so for 8 mg, okay, so 8 mg, this is the horizontal axis. So this would be So this angle, okay, so this is alternating angle. So this is going to be theta. This is going to be 90 minus theta. Okay. And then uh, for F, it is, let me see, Mm, yeah, F is just theta because it's similar triangles, if you can see. Yeah. So yeah, let's equate it. So first, we're going to equate the upward force first. Okay. So upward force, that's just the vertical component of F. So F sine theta, that is equal to 8 mg, which is downwards. So 8 mg sine 90 minus theta. So sine 90 minus theta. Okay, if you don't know the identity, okay, we say this is theta, this is AB. So sine theta here is, oh wait, sorry, this one is B, the hypotenuse. Opposite over hypotenuse, A over B. And since this one right angle triangle, this one is 90 minus theta. Okay, so theta now is going to be uh wait. Oh wait, theta now is, okay, so now it's C. So now sine 90 minus theta is C over A. And then for C, we know that it's just B square minus A. B square minus A square over B. Okay. Okay. Um, oh wait. Now there's one more force that we haven't accounted for yet. Okay, never mind. Let's not do it this way. Let me redraw the forces again. Yeah, so as usual, you have your friction acting upwards. You have your weight acting downwards, which is mg, and you have the normal contact force. So these are your three forces that you always have to draw when you like have a rough lane. Okay, so normal contact forces are okay, and now we are going to take it like with respect to the uh slope. Okay, so the vertical component will be relative to the slope. Yeah, so let me just redo again. Yeah, then you don't need all this complicated identity. Okay, so okay. Um, yeah, let me erase. By the way, the identity is probably for tangent theta, but okay, whatever. Yeah, so we're going to take the vertical force relative to the orientation of R and the slope. Okay, so vertical force, the component. Let's take the upward components first. So upward component is just R. So R, that is equal to mass. So this one, the angle here, if you do a bit of simple maths, like you draw the triangle, this one you get 90 minus theta, this angle. And then since this one right angle, this angle here would just be theta. Okay, so this is just going to be mg theta equal to mg cosine theta. Okay. And then downward also got this force, 8 mg Newton, and then theta, then downwards it would be 8 mg sine theta. So plus 8 mg sine theta. Yeah, that's all. Okay, yeah, so this is our equation 1. Now we are going to do for our horizontal with respect to um the slope. Yeah, so the slope, we have F to the right, and we have mg and the 8 mg to the left. So friction equals to mg. This one is just going to be mg sine theta plus this one is going to be 8 mg cosine theta. 8 mg cosine theta. Okay. All right. Now we're going to use the F equals mu R. And mu we already know it's just 0.5. So just going to write it as half. So it's just half R. And half, so we get half R equals to all these. And we already have another equation in terms of R, which is up here. So yeah, just sub 1 into 2. So half mg cosine theta plus mg sine theta equal to mg sine theta plus 8 mg sine theta. Okay, now let's expand everything and try to simplify. Plus 4 mg sine theta equals to mg sine theta plus 8 mg sine. Wait, let me see if I got copy anything down wrongly. Oh yeah, I did, unfortunately. This one is supposed to be cosine. Yeah, cosine theta. Okay. Okay, let's move this over to the other side as well as factor out mg and cancel out the mg from both sides. So 4 mg minus 1 mg is 3 mg, so 3 mg sine theta, or just 3 sine theta equals to 8 mg cosine theta minus half mg cosine theta. That should be 15 over 2 mg cos theta. So 16 over 2. Yeah. mg cos theta, mg cancel out, you just get cosine theta. Okay? Okay, now we divide by cosine theta on both sides. So cosine theta cancel out, sine divide by cosine, you get tangent. So 3 tangent theta was to 15 over 2. And then tangent theta, you get 15 over 2 divided by 3. So 15 over 2 times 1 over 3, you get tangent theta equals to 5 over 2. So yeah, just take the inverse tangent. And in this question, theta is given in degrees. So you have to make sure your calculator is in degree mode. Okay? Okay. Tangent inverse 5 over 2. You get 68.2 degrees to 1 decimal place. Yeah, so this would be our final answer for this entire question. Let's move on to the next question. Okay, so for this question, we are told that a particle A of mass 2.5 kg is released from rest from the top of a smooth plane, which makes an angle of sine inverse 0.2 with the horizontal. Okay, so we are gonna have to sketch all this out later. Okay, and then the particle A collides 2 seconds later with a particle B. Okay, of mass 3 kg, which is moving up a line of greater slope of the plane. Okay, so they're moving in opposite directions. So this is our plane. I'll just call this theta. So from the top, we have A. So A is 2.5 kg. Wait, sorry, kg. Released from rest. And then B. Okay, so A is going down. And then B, which is 3 kg, is going up the slope. Okay, and then it also says the speed of B immediately before the collision is 3.5 meters per second. So this is the speed of B immediately before the collision. Okay, and immediately after the collision, B has a velocity of 0.5 meters down the plane. Okay, so after, after I'll just draw like as if it's horizontal. So B is now going 0.5 meters per second. And A should be logically also going down. And we are going to, oh, never mind. Okay. So they told us to find the distance A. The distance A moves up the plane after the collision. So that means logically A must be moving up. Yeah. Yep. So this is our after, and this is before. Okay. All right. So yeah, these are all the information that we have. Okay. So let's let the speed of A, like right before the collision, be U. Okay. So we are told that particle A collides 2 seconds later. So the later is with reference to the time that it's released from rest. So rest, the initial speed is of course 0. So yeah, this is the, yeah. All right, so to find the speed, we need to know its acceleration, okay? So to know the acceleration, okay, so it's a smooth plane. So the only force that should be acting downwards, okay, so let's draw a little force diagram. So for A, only the weight is acting, there's no friction. And consequently, there's also the normal contact force R. Okay, so R is equal to this vertical component of mg with respect to the slope. So that is just mg cos theta. I'm not going to show how you derive the angle. We did that in the previous question. Yeah, so R is equals to mg cos theta. So the force that is causing it to go downwards is actually the horizontal component of mg, which is mg sine theta. Okay, so to find the acceleration, we're going to use F equals to ma. So F equals to ma. So F is mg sine theta. Okay, and ma. So even though we know what m is, I'm just going to let it be equal to m. So m cancels out. So we get a is as g sine theta. And sine theta, we already know sine inverse 0.2. So sine theta is just 0.2. So this is 0.2 g. Okay. Yeah. So u just going to be the initial speed, which is from rest. So 0 plus at. So a is 0.2 g times t. So t is 2 seconds later. So 0.4 g or 4 meters per second. So this is the speed right before the collision. Yeah, so now we can use our conservation of momentum. So yeah, here it's a bit complicated since like the particle, they're not like moving in one direction. One time is they're going towards each other and then they're moving away. So we have to decide which direction is positive, which direction is negative. So I'm going to choose down the slope as positive and up the slope as negative. Okay, so initially we have A moving down the slope, so m times u. So 2.5, that's m times u, which is 4, minus, so B is moving up at that instant. So that is 3, which is m times v, which is 3.5. And that is equal to the total momentum after. So after the collision, B is moving downwards. So B, yeah, B is 3 kg. So 3 times 0.5. And A is moving upwards. So A is, wait, where's A? Oh, wait, what am I saying? Sorry. Okay, yeah, A is 2.5 V. So we don't know what V is. So that's what we have to find. Okay. Yeah. So, yep. Let's find out what V is. This is one of the most long, like one of the longest papers I've ever done. Like all the questions are not like short answer only. There's a lot of thinking involved. Okay. Minus 2 and V is 2 divided by 2.5. You get V equals to 0.8 meters per second. So yeah, we got our final value of A. And now using this, we can find the distance that A moves up the plane. So to find that, we know the initial speed, which is this, as well as the final speed. So if you visualize it, like right after the collision, A would, just move up the plane and then it'll start to go down. So we just want to calculate the distance it moves up the plane. So the final speed would be 0 because at the instant it stops moving up, it's going to stop instantaneously. So final speed is 0. Okay. And since we know the final and initial velocity, as well as the acceleration, which is just this, but now since, the movement is opposite to the direction of acceleration, it's negative. So important, okay? So it's minus A. Yeah, so go to your MF19, go to your Suvat formula, look for the formula that fulfill all the criteria. And yeah, so we can use this formula v squared equals to u squared plus 2as. So I'll just write v1 squared equals to u squared, which is our v squared, minus 2as. Yeah, I just put the minus sign in front so that like we don't have to put the minus sign into our a. Okay, now we're going to make s the subject. So v squared minus v1 squared and s, what's going on? Oh, sorry. Okay, and then s would be, okay, it's lagging a bit, equals to v squared minus, oh no, v1 squared over 2a. So v squared is 0.8 meters, 0.8 square. V1 square, that's basically just 0. So 0 square over 2a. So 2a, that is 0.2 g. So 0.2 g, g equals to 10, so you just have 2. Yeah, and then 0.8 square over 2 times 2, you get 0.16 as the distance. Yeah, so this is our final answer, 0.16 meters. Let's head on to the next question. Okay, so for this question, we are told that particle P starts from a point O and moves in a straight line. Velocity v meters of P at time t seconds after leaving O. So t is the time, like t is the time after it leaves O, is given by this expression in terms of t. Okay, let me just remove that. Yeah, so this is the expression. And for the first part, we need to find the acceleration of P when t equals to 2. Okay, so if we're given V in terms of t, and we need to find the acceleration, we are going to use the expression that acceleration is just the derivative of V with respect to t. So it's just dv dt. Okay. Okay, so let's expand it. Okay. So v 2t minus, so 2t times t, that's 2t cubed. 2t times minus 4, that is minus 8t. Minus 3 times t, that's just minus 3t. Minus 3 times minus 4, that is plus 12. Okay, now we shift it over. So 2 over 3 t cubed minus 8t minus 3t, that's minus 11t. So minus 11 over 3t plus 12 times 1/3, that is plus 4. So this is our expression for V. Now we can finally get the expression for A. We'll just have to differentiate lah. Okay. Okay, so differentiating, just bring the power to the front. So 3 times 2/3 and minus 1 from the present power. So you get 2. And for this, you do the same. You just end up removing t. And then the constant term just vanishes. Okay. So you get 2t squared minus 11 over 3. Okay. And now just sub t equals 2 to get your answer. So you get 2 times 2 squared, so just 8. So 8 minus 11 over 3. 8 minus 11 over 3, you get 13 over 3 meters per second square. Yep, so this would be our final answer for the first part. Let's move on to the next part. Okay, so before I continue over to part B, I made a silly mistake in part A. So I expanded it wrongly, more like I copied it down wrongly. So yeah, this is supposed to be t squared, not cubed. I don't know why I put cubed. Okay, so it's 2. But then here I put squared. What? Wait, no. It's just supposed to be t. Wait. Yeah, so this is t. So that is, so this one is 3, then 2. Yeah, okay. And then this one is just 2. So this one is 2 times 2 third. You get 4 over 3. Okay, and then this, no. Okay, and then this one is 4 over 3. So 4 over 3 times 2 minus 11 over 3. Yeah, you get -1 as your final answer. Sorry for that mistake. Yeah, so yeah, this is our final answer. Let's move on to the next question. Okay, so let me put, yeah, so in part B, we're told to find the total distance traveled by P in the first 3 seconds of its motion. Okay, so to find the total distance, we need to know the expression for displacement, or S. So relating displacement to velocity is just the integral of velocity with respect to time. So yeah, let's integrate it. So it's 2 third t square minus 11 over 3 t plus 4 dt. So integrating this, you move the 2 over 3 out and you just integrate t squared. So you get t cubed 2 plus 1, and then you divide by the new power 3. Minus, yeah, again, ignore the 11 over 3 and you integrate just t only. Then you would get t squared over 2 plus 4, just add the t plus c. And you get 2 over 9 t cubed minus 11 over 6 t squared plus 4t plus c. Yeah, so this is the expression for S. So we have this unknown constant, all right? So we have to find what C is. So yeah, we know that particle P starts from point O. So at point O, the displacement is 0, and time t is the time after leaving 0. So obviously then t is equals to 0. So S is equals to 0 when t is equals to 0. So you substitute that, you'll just get that c is equals to 0. Therefore, S is just 2 over 9 t cubed minus 11 over 6 t squared plus 4, oh shoot, 4 t. Yeah. So now we're going to
find the time at which v equals to 0, because at the point when v instantaneously stops, it changes direction, which affects the displacement. So at those points, our displacement, like after those points of inflection, our displacement won't equal to the total distance traveled so far. Yeah, so let's find the values of v. Okay, so just equate it to 0 using the factorized form. It's a lot easier. So 1/3 times 2t minus 3 times t minus 4 goes to 0. Then you get t equals to 3/2. So these are inflection points, and t equals to 4. Yeah. So yeah, these are our points of inflection. So now we're going to roughly sketch out the path. So this is our initial point at t equals 0. And let's say it moves here. And this is the first inflection point at t equals to 3/2. And then, I don't know, travels for a while. And then this is, let's say, at t equals to 4. And then it goes, yeah. So this is the rough path of P. Yeah, so they asked us for the first 3 seconds, and unfortunately that's within one of the inflection points. So we first have to find the displacement at this inflection point, and then find the displacement at t equals to 3. And then you take the difference between these two inflection points to get that distance, plus the displacement at the first inflection point. Okay, so we're going to sub E equals to 3/2. So S is going to be 2/9 t cubed, 3/2 cubed, minus 11/6 t squared times 3/2 squared plus 4t plus 4 times 3/2. Okay, and then just substitute minus 11/6, 3/2 squared plus 4 times 3/2. Yeah, that's 21/8. Yeah, so this is the displacement at that point. Now, we're going to sub t equals to 3. Okay, so t equals to 3. So we get S is equals to, I just substitute t equals to 3 cubed minus 11/6, 3 squared plus 4 times 3. Okay. Okay, so this one is 3/2 meters. Okay, now the total distance. So the total distance would be the distance, the displacement at t equals to 3/2. So 21/8 plus the difference between the displacement at t equals to 3/2 and the t equals to 3. So plus 21/8 minus 3 over 2. So you would get 15 over 4, or 3.75 as your final answer. Yeah, so this would be our final answer for this part. Let's move on to the next question. Okay, so for the final part, we need to determine whether P returns to O. So we have to take note of the fact that when P returns to O, the displacement is going to be 0. And since we have the displacement like expression in terms of T, we can just equate it to 0 to find out, okay? And see whether it fits our domain for T. Okay, so let's copy it down. Minus 11 over 6t squared plus 4t equals to 0. Okay. Now we're going to factor out 1 over 9. I think, yeah, 1 over 9t. So this is going to be 2t squared minus 11 over 6 divided by 1 over 9. That's minus 33 over 2t. 4 divided by 1 over plus 36 equals to 0. Yeah, so you'll get 1 over 9t equals to 0. And then you'll get t equals to 0, which is obviously not what we're looking for, because obviously at t equals to 0, it's at O. So yeah, we have to solve this equation. Or instead of solving it, we just want to know whether P returns to O, right? Wait, let me see if there's any domain. Okay, there's no like range for T. So we just have to find out whether this equation has any real solutions. And to do that, we can just simply use B squared minus 4AC. And if it's more than 0, we can say that, there's real solutions, and therefore P does return to O. Okay, so let's find out B squared minus 4AC. So B is minus 33. Sorry, minus 33 over 2 squared minus 4 times A, which is 2, and C, which is 36. Okay, so minus 33 over 2 squared minus 4 times 2 times 36. Yeah, we got a negative answer. Yeah, so, sorry. Oh no. Okay, so 63 over 4. Okay, so we can say that the equation above has no real solutions. Above has no real solutions. Hence, P doesn't return to O. P doesn't return to O. So yeah, this would be our final answer for this part as well as the entire question. Let's move on to the last question. Okay, so for this final question, we're told that a block A of mass 2 kg, particle B of mass 0.5 kg are connected by a light inextensible string inclined at 15 degrees to the horizontal. So this is the string. They are pulled across a horizontal surface with acceleration 1.2 meters square by a force of magnitude 6 newtons. So the acceleration is 1.2 meters square, meters per second square, applied to A, acting at 20 degrees above the horizontal, as shown in the diagram. The string and force applied to A are in the same vertical plane. Okay. All right. And the contact between B and the surface is smooth. Contact between A and the surface is rough. So rough, you should immediately think of friction. So that means there's friction acting between A and the surface. So obviously, since it's moving in this direction, the friction between A is in this direction. So FA. Okay, so first part, we need to find the tension in the string. Yes, so this is the string that they're talking about. All right. So, okay, so to find that, okay, let's label all the forces that are acting. So obviously we have the weights of B and A. So B is 0.5 kg times A, which is G, and then A is 2 times G. And then we also have the normal reaction forces, which is obviously just equals to their weight. Yeah, okay. And okay, sorry for the delay. So yeah, as I was saying, we need to find the tension in the string. So since both of these two particles are connected, yeah, there's obviously tension in the string. So from the perspective of block A, it's gonna be here. So this is T. And then from the perspective of block B, it's gonna be here. Yeah, so okay, so now we need to find the tension in the string. Okay, so the way we can do this is to separate and isolate the two systems. So you can isolate A and treat it as its own system. You can also what? Sorry. Okay, so yeah, so we have to separate the systems. So for B, this is going to be something like this. Okay. Yeah. So yeah, we're going to take B, all right? So yeah, I'm just going to draw it here again with B only this time. So the forces acting on B are its weight, which is the mass 0.5 grams, sorry, times G, and it's RB, the force acting up. Okay. And oh my gosh, wait, sorry. Oops, okay, yeah. So the force acting up and the tension acting at an angle 15 degrees. Okay, yeah, so as I was saying, this is our diagram. And now, yeah, so we're just going to focus on the horizontal component since we know the acceleration of it. And in the horizontal direction, only the horizontal component of the tension is available. So it's going to make things a lot easier. Okay, so yeah, let's start. So we're going to use F equals to MA. So in this case, our F is going to be the horizontal force, which is the horizontal component of the tension, which is T cosine 15 degrees. So T cosine 15. So mass is 0.5 and acceleration is 1.2. And then T would just be 0.5 times 1.2, that's 0.6 divided by cosine 15 degrees. Okay, just type it into your calculator. You would get 0.6 21 newtons as your final answer. Yeah. Yep. Yep. Yeah, that's gonna be our final answer for the first part. Let's move on to the next part. Okay, so for the final part, we have to find the coefficient of friction between A and the surface. Okay, so for this question, let's see what we have to do. Okay, so if we take A separately, um, yeah, if we, yeah, let's just take A separately because if we take the whole system, we'd have to also find RB, which would make things a lot more complicated. So let's just take A as its own system. Okay, so I'm just gonna redraw A, this time as a particle. Okay, so the forces acting are the weight of A, so that's 2G, and RA, and yeah, 6 newtons pulling force, 20 degrees. Okay, what else we have? And then, of course, the pulling force at 15 degrees. So the tension, this is at 15 degrees. And what else? And lastly, we have the friction. So friction, I'm just going to put it here, FA. Yeah, so these are all the forces that are acting. So to do this, we're going to first take the vertical components because we know that it's moving, towards the left. So since it's not moving vertically, the vertical forces must be in equilibrium. Yeah, so let's do that. So for the vertical components, we have 6 Newton, sine 20, that's upwards, as well as RA. And for downwards, we have the 2G and the vertical component of T, which is just T sine, yeah, sine 15. Wait, is it T sine 15? Yeah, T sine 15. Yeah, so RA plus 6 sine 20 degrees is equals to 2G plus t sine 15 degrees. Okay, and then the RA, we can re-express it using F equals to mu R. Okay, never mind. But that we're gonna leave it for the next equation. Yeah, let's make RA the subject now. So now RA is equals to 2G plus T. So T is 0.6 over cos 15. So 0.6 over cos 15 times sine 15. That's 0.6 tangent 15 minus 6 sine 20 degrees. So this is RA. So this is equation 1. Okay, now let's make an equation for the vertical side. So for the vertical side, remember it's not in equilibrium, so we have to use F equals to MA. So let's find our F for the horizontal, okay? Like a horizontal resultant force, basically. So it is moving in this direction. So any force to the left that's horizontal, it's going to be positive. So to the left, we have the horizontal component of 6 newtons. So it's going to be 6 cos 20. So the 6 cosine 20 minus, to the right, we have the horizontal component of t, which is t cosine 15 degrees. And we have minus Fa, which is the friction that's acting between A and the surface. Yeah, okay. Okay, so now we'll use our F equals to MA. So this is 6 cosine 20 minus T. So T cos 15. If you substitute this expression, it is just going, okay, never mind. Let's just cancel it out. Yeah, 0.6. Yeah, minus Fa. So Fa, we can use Fa equals to mu times Ra. So we can substitute that. And that would be equal to mass times acceleration. So mass is 2 and acceleration is 1.2. Yeah. Okay. Okay, let's now, this is equation number 2. So now we're going to sub 1 into 2. So 6 cosine 20 degrees minus mu times RA. So RA is 2G plus 0.6 tangent 15 degrees minus 6 sine 20 degrees. Yeah, this one is equals to 2 times 1.2 is 2.4 plus 0.6, which is 3. Sorry. Okay. Yeah. Yeah, now we're going to make mu the subject. So we'll isolate the mu term. So 2G, we're gonna write this 20 plus 0.6. Yeah, I'll just keep everything exact, because that's the way I like to do it, so that we don't make any rounding errors. Okay, and then this one would be equals to 6 cos 20 minus 3. And then mu would just be 6 cosine 20 degrees minus 3 over 20 plus 0.6 tangent 15 minus 6 sine 20 degrees. Okay, let's see. You're gonna substitute into the calculator. Just type it directly in. 20 plus 0.6 tangent 15 minus 6 sine 20. And we get 0.146. 0.146 as our final answer to 3SF. And with that, we have also come to the end of this paper. So I hope you found this video helpful. If you did, please make sure to like and subscribe for more future videos on A-level maths and further maths past papers. If you have any feedback or any future video ideas or what you want me to, improve on, like anything, please leave them down in the comments below. And I'll see you again next time. Okay, thank you.